Let's take a look at some of the things that can happen because of special relativity. And the first is going to be time dilation here. So let's actually take a step back and remind ourselves of where we're at. So we know that the speed of light is a constant regardless of your reference frame. So no matter how you're moving, what you're doing, any of that sort of stuff, if you try and measure the speed of light in that frame of reference, no matter where the source is, no matter how the source was moving, you'll always get the same number. And everyone else will also get the same numbers. That means if I'm riding on a train and I turn on the flashlight and I measure how long it takes the light to travel from me to the end of the train car, I'll get the speed of light. If someone's standing next to the train and they measure that same thing, they'll get the same measurement. And then we also believe that the laws of physics should be the same kind of regardless of reference frame, because otherwise they're not useful. So when we combine those two things, we get stuff like time dilation. So to describe some of the stuff that's going to come up here, I want to just define a few terms. The first is a proper measurement, and this is a measurement taken in the same frame of reference or reference frame as the event or events. So if you're measuring the length of something, you need to be moving at the same speed as that object to get the proper length. It's a little weird for time, but for time, this is the frame of the, it should just be the frame of reference for the starting and ending positions. So if we have, say, a race that someone's running, then the proper time would be the time that's measured by whoever is standing or moving at the same speed as the starting and ending positions. We're not going to worry about if the starting and ending position have different reference frames. For this, we're going to assume the starting and ending positions are not moving relative to one another, and therefore all of our calculations will be a little bit easier and all of our vocab will be easier to use. Observed measurements are measurements taken in a different reference frame. So this would be, say, the reference frame of the runner in a race, or this would be the reference frame of someone standing next to the train, that sort of thing. Relativistic factor, this is just a term that's going to come up, and it's a constant that I'll show you later. It's based on the relative speeds of two reference frames. So we use the Greek letter gamma to talk about the relativistic factor, and it's just a number that we use that makes it easier to do kind of some of the other calculations. So let's get into time dilation here. And we'll take a bit on this because it's weird. It's the weirder of the two, and we'll kind of make sense of it together. So what we have on the left here with the astronaut is the simplest kind of concept of a clock that you can make. So a clock is something that just measures the time that passes between two things, right? Well, how do we make a clock? We have to have something that repeats and takes the same amount of this abstract concept of time. So if you have a pendulum swinging back and forth, that pendulum has a constant back and forth motion. So the same interval, like if I have a swing here to here, the same amount of time is going to pass as, 5,000 swings later from here to here. So what we have here is an even simpler clock. It's just a light source that shines a light to the mirror and it bounces back and hits the receiver. And we're just going to say each one of those intervals is 1 second, just for sake of discussion here. Maybe it's way less than a second, but we can then just imagine, for a second we have to wait for 1 million of these to pass, or whatever it is. But we're going to say our second is the time it takes for light to travel to the mirror and back. Mirror and back, mirror and back. So there's two events, light leaving the clock, and the second event, light entering back into the clock. Those will happen at the same point in space and different points in time, basically. So light leaves, light comes back. The time between those two events, the interval between those two events, is what we're calling 1 second. So now, if we look at that, how long does that actually take? Well, it's going to take delta T naught is equal to 2d over c. Because how far does it have to travel? To the mirror and back. So 1 second is 2d over c. Or the other way you can think about it is, if we want this clock to measure 1 second, how far would d have to be? Okay. So this is pretty, hopefully, straightforward from the astronaut's perspective. But let's talk about someone who's standing on Earth and this space shuttle is, say, moving with some high speed. Well, on Earth, what they see is the light leaves the sensor. We still have to agree on events occurring, right? So the light has to leave the sensor, hit the mirror, come back to the receiver. But by the time the light gets to the mirror, the space shuttle has moved, and so now the mirror is here. And then by the time it gets back to the sensor is over here. And so what happens is we've moved, and we have, in this case, we think that 1 second is actually 2s over c, right? Because it moves here and back. And so it takes this whole path, s to s. Now, if we look, we can use Pythagorean theorem to find how s, d, and l are related. And l is just the distance between, or the distance that this spaceship travels. And so I'm not quite sure why they have L equals V delta T over 2. It makes a lot more sense just to say L is equal to V delta T. Oh, it's because of the Pythagorean theorem down here. So we'll scratch that. Sorry, I forgot there was a reason for that. So S is equal to D squared plus L squared square rooted. And we can see from inspection then, and just also by knowing the geometry here, this delta T, 1 second on Earth and 1 second on the spaceship, won't match up. We won't both think that the same amount of time passes between when the light leaves the sensor and when it, light leaves the light bulb and when it's received by the sensor. More time is going to pass on the spaceship, more time is going to pass on Earth than on the spaceship, because this S is longer than that. So the other way of thinking about it is, on the spaceship, they'll think 1 second has passed. On Earth, we'll think maybe 1.5 seconds have passed. So what this means then is time is passing slower on the spaceship than it is on Earth. From Earth's perspective, I should clarify that. So from Earth's perspective, less time passes on the spaceship when it travels between here and here than it passes on Earth. Because we know on the spaceship has to measure 1 second between these intervals. But on Earth, we measure a longer than 1 second because it has to travel this longer path. Now, normally this wouldn't be a problem in kind of classical physics because we would say that, oh, the light just goes faster because it's got the motion of the spaceship added to it. So it actually goes faster and we get 1 second green. But remember, with special relativity, we say the speed of light has to be a constant. So I have 2s as my distance, but I can't increase the speed at all. The speed has to stay at c. Now, if we run through kind of relating these two times to each other, so if I want to find how delta t naught is related to delta t, we can do some algebra that I'm going to skip past, but it's equal to this equation here. And this basically comes from this d, if you solve for s, and put in the L being v delta t over 2, solve this s for d, plug it in, and then you can kind of rework this. So this one should be a proper time. So this right here is the proper time. This right here is an observed time. So remember, proper time is the time is a measurement taken in the same frame of reference as the events. So in this case, the event is the light source turning on, and the event is the light source hitting the mirror. The event is the light hitting the receiver. So all of those are happening on the space shuttle. So any measurements taken on the space shuttle are proper measurements. So this is the proper time. D is our proper distance. Anyone watching it who's moving relative to the space shuttle, so from the space shuttle's perspective, this observer is moving. That means this is an observed time because we're not moving along with these changes. So that gives us, like I said, this relationship here, that if we take the proper time and we divide by this factor here, that's basically how quickly is the space shuttle moving, we can get the observed time. The other way that this equation can be rewritten is because we can know that, and I'll define gamma for you. So gamma is 1 over the square root of 1 minus v squared over c squared. So we can also say that the equation for time dilation is as follows. Gamma times the proper time equals the dilated time, or how long it passes in another frame of reference. So this tells you the relationship between, if v gets really close to c, it's never going to actually reach c, but it gets really close to c, this becomes a really, really small number, which means gamma becomes very, very big. So that will wrap up kind of the initial thoughts here. We'll do some examples in the next video.